All right. So we've moved on to Chapter 5, Section 5. And in this section, we're going to be looking at calorimetry. And calorimetry is simply measuring how much heat is either given off or absorbed in a particular chemical reaction. So, we don't know the exact enthalpy of the reactants and products. We can get some of that information. We can get some of that information by looking in tables, but somebody has to come up with these numbers originally. And so the way that we do that, as I mentioned, is through a process that we call calorimetry. And it's just a matter of measuring how much heat flows into or out of a particular equation. So, how did they come up with these numbers? They did calorimetry. So what we're going to do is we're going to look at two different types of calorimetry. The first type of calorimetry is called constant pressure calorimetry. I guess before we do that, we need to look at two things here. One is a term that we call heat capacity. Heat capacity is the amount of energy required to raise the temperature of a substance by 1 Kelvin or 1 degree Celsius. Since a 1 Kelvin change in temperature is equal to a 1 degree Celsius change in temperature, these are interchangeable. So we refer to that as its heat capacity. This is an extensive property. If you have twice as much of the substance, your heat capacity will be twice as high. If you don't want an extensive property, you can divide by the number of grams, and that will give you the specific heat capacity. Sometimes that will be referred to specifically as the specific heat, and it is simply the amount of energy required to raise the temperature of 1 gram of a substance by 1 Kelvin, or 1 degree Celsius, if we wish. All right, so and the reason I mention this is that we're going to use specific heat for one thing and heat capacity for the other thing when we talk about calorimetry here in just a moment. All right. So specific heat, we've actually already seen this formula in a slightly different form a little bit ago. Specific heat is the heat transferred divided by the mass times the temperature change, whereas heat capacity is just the heat transferred divided by the temperature change. All right. For specific heat, it's S is equal to Q, which is the heat, and M is the mass, and delta T, of course, is the change in temperature. We saw this earlier when we were looking at heat energy earlier in the chapter, and the equation was Q is equal to M times S times delta T. I believe in your textbook it lists specific heat as C sub S. And so it is a little bit different in your textbook, but most textbooks will use S. All right, so we're going to be looking at something that we refer to as constant pressure calorimetry. And constant pressure, as the name implies, it is done at constant pressure. That pressure is atmospheric pressure. So we'll do it at constant pressure. The setup for it is pretty simple, which makes it really affordable to do constant pressure calorimetry. So here we've got, usually we'll just take 2 nested coffee cups, and the coffee cups are made out of styrofoam. And as you know, styrofoam or polystyrene is a very good insulator of heat, and so that keeps the heat in when you're doing your chemical reaction. Typically, you'll have a thermometer. You have to have a thermometer, otherwise you're not doing calorimetry. You're just mixing stuff together. And then sometimes you'll need like a glass stirrer, or sometimes you'll use a metal stirrer. It doesn't particularly matter. When we do this in the lab, we actually just stir it with our thermometer because we're stirring very gently. You'll see on this one, it's got a glass, or not a glass, but a cork stopper. The cork stopper is just to keep heat from coming out. And it's just kind of like when you're using a coffee cup, you'll put a lid on it, and that keeps your coffee hot longer. However, you'll find that heat will seep out of your coffee cup. All right, so you're limited into the type of reactions that you can do. You need, if you're going to do constant pressure calorimetry and you're going to use coffee cups, you need to use solvents that are compatible with polystyrene. And polystyrene is quite compatible with aqueous solutions. Both acid and base are just fine for polystyrene, for styrofoam. You can't use, you could use something like alcohol because alcohol will not affect the polystyrene, but you couldn't use something like a nonpolar solvent like benzene or acetone or turpentine or anything like that. Gasoline. If you've ever taken any of those solvents and put them into a coffee cup, you'll find that the coffee cup will dissolve, and that's just how that works. So you're limited to very polar things like water. All right. So you just carry out the reaction in an aqueous solution. You measure the heat change on that solution, and any of the heat that was produced by the reaction is absorbed by the solution. And I'll show you the math for that in a minute. We use the assumption that the specific heat of the solution is the same as the specific heat of water, and that is almost accurate. It's a good enough approximation. All right, so we're going to switch over to number 53 on our in-class assignment. Let me clear all that out. So number 53, and it says, when a 9.55 gram sample of sodium hydroxide dissolves in 100 grams of water in a coffee cup calorimeter, the temperature rises from 23.6 to 47.4 degrees Celsius. Calculate delta H in kilojoules per mole of sodium hydroxide for the solution process. Well, the first thing that we want to do before we start actually calculating anything is we want to understand sort of the basics of this, and that is that the Q of our solution is going to be equal to the negative the Q of our reaction. So the Q of our solution is equal to negative the Q of the reaction. Whatever heat is produced by the reaction is going to be absorbed by the solution. Now, some of that heat will be absorbed by the coffee cup, but for simple calculations like this, we can ignore that heat because the coffee cup does not absorb a ton of the heat. So we'll say that the Q, and I'm going to abbreviate solution to SOLN here. The Q of our solution is going to be equal to the mass of our solution times the specific heat of our solution, and we're just going to use water specific heat there, times delta T. Our mass of the solution, and we do want the entire mass, so we've got 9.55 grams of sodium hydroxide and 100.0 grams of water. So we're going to put in 109.55 grams of our solution. The specific heat is that we're going to use is the specific heat of water, 4.184 joules per gram degrees Celsius. And one thing to remember about this is that per degree Celsius, that is a change in temperature. So we don't need to do any sort of weird conversions here. All right, and then we're going to multiply by the change in temperature. Our change in temperature here, we'll do final minus initial, 47.4 degrees Celsius minus 23.6 degrees Celsius. All right, and then that difference is our delta T. All right, so 109.55 times 4.184 times, and we'll go ahead and put this difference in, 47.4 minus 23.6, and that gives us 1,908, and I'm going to write that in scientific notation. So Q of our solution is equal to 1 point, and we only have 3 sig figs here because of this. So 1.09 times 10 to the 4 joules. So 1.09 times 10 to the 4 joules. All right. Well, since Q of our solution is negative the Q of our reaction, that means that Q of our reaction, and I'm going to just put RXN for reaction, Q of our reaction is equal to negative 1.09 times 10 to the 4 joules. All right. And since we want this in kilojoules, I'm going to take that and divide by 1,000. So that's going to give us negative 10.9 kilojoules. So negative 10.9 kilojoules. All right. So now what we want to do is we want to calculate delta H. So delta H is Q at constant pressure. But we want the delta H in kilojoules per mole. Right now we just have it in kilojoules. We want it in kilojoules per mole. So we're going to do the Q of our reaction, RXN, over the number of moles of sodium hydroxide. All right, so now delta H is equal to negative 10.9 kilojoules. And we've got 9.55 grams of NaOH. And then we've got 40.00 grams, this is the molar mass, of sodium hydroxide per mole of sodium hydroxide. You'll see the grams of sodium hydroxide cancel out, and that will give us kilojoules per mole. So we'll clear that, and we'll do negative 10.9 times 40.00 divided by 9.55. And that gives us negative 45.7 kilojoules per mole. All right, and that is how we solve a coffee cup calorimeter or constant pressure calorimetry problem. All right. So we'll switch back over, and we're now going to look at bomb calorimetry. When we're doing bomb calorimetry, it's a little bit different. In bomb calorimetry, we take our chemical reaction. It doesn't have to be in aqueous solution. We just take our chemical reaction. It's going to be usually a combustion analysis. So we're going to take it and burn it. But we'll take whatever our chemical is and put it into a small cup, and then we will fill this bomb, the reaction chamber, with oxygen gas. And so we seal it up with oxygen gas, get rid of, purge out carbon dioxide, so we just have oxygen gas in there. And it's important to have enough oxygen to completely consume anything that's present. You don't want any of your material left over when you're done. You want it all to burn. We seal it up, and then we have these electrical leads that go in there. The electrical leads are just for causing a spark. That spark will help to ignite the combustible material. We submerge our bomb, our reaction chamber, into a large water bath that is in a huge vessel. And then we will allow heat, or heat will flow from our hot burning vessel, burning material inside the vessel, into the big water vessel. You'll see there's a stirrer, and there's also a very fine thermometer that allows us to measure the temperature. And then based on how much the temperature of our calorimeter increases, we can calculate how much heat was given off by this. So again, the reaction's carried off in a bomb. It's usually going to be something like combustion. right? Now, one thing that's a little bit different is because this is at constant volume, it's not going to be at constant pressure because some of the oxygen will get consumed, you'll produce carbon dioxide. So it's likely that the pressure inside of here will change, and we'll assume that it will change. What you're actually measuring is heat at constant volume, not heat at constant pressure. So really what you're going to get is delta E, the change in internal energy, instead of delta H. But as we've seen before, usually that's a pretty small difference. So I want to show you how it is that we go about calculating the heat for a bomb calorimeter. All right, so we'll go back over and we'll look at the next problem, number 55. And on number 55, here we've got a 2.200 gram sample of quinone is burned in a bomb calorimeter whose total heat capacity is 7.854 kilojoules per degree Celsius. You'll notice that's not specific heat, that is the heat capacity of the calorimeter. The temperature of the calorimeter increases from 23.44 degrees Celsius to 30.57 degrees Celsius. What is the heat of combustion per gram of quinone and also per mole of quinone? So like before, I want to set up how we're going to do this. We'll have Q of our calorimeter, and that's equal to negative the Q of our reaction. So Q of our calorimeter is negative the Q of the reaction. The Q of our calorimeter is going to be equal to the heat capacity of our calorimeter. We'll use the uppercase C for heat capacity, times the change in temperature. You'll notice that we don't have mass in here, so that's because the heat capacity of the calorimeter, it's not per gram or kilogram, it's the heat capacity of the whole calorimeter. The heat capacity of our calorimeter here is given as 7.854. So 7.854 kilojoules per degree Celsius. And then we'll multiply by that change in temperature. And the change in temperature is going to be 30.57 degrees Celsius minus 23.44 degrees Celsius. Now, before we move on, I want to show you something about that change in temperature. So we'll do 30.57 minus 23.44. You'll notice that both of those numbers have 4 significant figures, but the difference at 7.13, and again, with subtraction, it's the place, so hundredths place, hundredths place, hundredths place there. So what we're going to find is that the delta T only has 3 significant figures. So we need to keep that in mind when we're doing this calculation. So we'll take that 7.13 and we're going to multiply that by 7.854. And that gives us 55.999 with 3 sig figs. We're going to call that 56.0 kilojoules. So 56.0 kilojoules. That means that the Q of our reaction is the negative of that. It'll be negative 56.0 kilojoules. All right. So now we've got 2 values for delta E that we want to calculate. So up here we've got delta E, and again, delta E is going to be the heat at constant pressure. This one is going to be per gram. So I'm going to put this below, per gram. I said delta E is heat at constant volume is what I meant to say. I think I said constant pressure. Delta E is the heat at constant volume. All right, so it's going to be Q of our reaction divided by the mass of our material, because we wanted it per gram of quinone. And I didn't want negative Q, I just wanted Q. Let me fix that real quick. All right, that fixed that. So here we've got negative 56.0 kilojoules, and we'll divide by 2.200 grams. All right, so let's clear all that. So negative 56.0 divided by 2.200, and that gives us negative 25.5, we'll round to 25.5 kilojoules per gram of quinone. All right. We also want to get per mole. So I'm going to put this one as per mole. Here we'll want the Q of our reaction divided by the number of moles of quinone. All right, so negative 56.0 kilojoules divided by 2.200 grams. All right, and I'm not going to put the entire formula there. The molar mass, because we want to convert that mass into moles, is 108. I did this a little earlier. 108.10 grams per mole. All right, so our grams cancel out and we'll get kilojoules per mole there. All right, and I could have just used that, but we'll go ahead and type it back in. So negative 56.0 divided by 2.200. All right, that gives us this part, and that's the number we just had. And we're going to multiply that number by 108.10. And with three significant figures, that's going to give us negative 2.75 times 10 to the third kilojoules per mole. All right, and that is how we do calorimetry. So we now want to look at a concept that we call Hess's law. We actually saw a little bit of Hess's law a little bit ago, but the way that Hess's law works is that we can add together chemical reactions, the thermochemical equations, to get thermochemical equations for things that reactions we haven't done. So we have people who measured chemical equations, who measured their delta H, and then we can add those equations to get new equations, and that will give us delta H for reactions we haven't done. All right, so there are some tricks to doing this, and this picture, what this picture is telling us is that if we want to get delta H for this reaction, which is the CH4 burning to produce carbon dioxide and water, that we can take the delta H for this reaction and the delta H for this reaction and add them together to give us the overall delta H. And that's what that is. So I want to show you an example of how to do this, a practical way to do this. So Hess's law, an example. Here we've got the enthalpies of a couple of reactions. So here we've got 2H2, so 2 moles of hydrogen plus 1 mole of oxygen gives us 2 moles of water vapor. You'll see the value is negative 483.7. We saw that a little earlier. This one, we've got 3 moles of oxygen gets converted into 2 moles of ozone, and we've got a value there of positive 284.6 kilojoules. From those, we want to calculate the delta H for this reaction. So to do this, we want to use a linear combination of these two equations that will give us this. If you've ever done the thing where you add together equations to solve for x or y, then this is essentially what we're doing. It's just a little bit more involved. All right, so here we go. What we want to do is we want to recreate this using the chemicals that are up there. Usually when I do this, I start on the left and work my way over. And if I get something that is in more than one equation, then I usually skip to the next thing. All right. So here we've got H2, so 3H2. And if you look, there's only one place that hydrogen is present in the above equations. It is on the reactant side, as is this one, but it's not the correct number. So what we're going to need to do is to take that top equation and multiply it by 1.5 or 1.5. Or if you want to think of it as 3 halves. So we'll multiply that top equation by 3 halves. When we multiply the top equation by 3 halves times 2 gives us 3. 3 halves times 1 gives us 3 halves. 3 halves times 2 gives us 3. So that took care of our hydrogen. To get the ozone, well, we look on our second equation and we'll see that ozone is there. But here you'll notice that the ozone is on the product side where we want it on the reactant side. Also, the number isn't the same. So we're going to need to do two things. One, we're going to change the direction of the reaction. And as you guys remember, when we change the direction of the reaction, we change the sign. But the other thing that we're going to do simultaneously is that we're going to multiply that equation by 1/2 to get it from 2 down to 1. So when we change the direction and we multiply by 1/2, we will find that, so the 3 times 1/2 gives us 3 halves O2, and the 2 times 1/2 gives us 1. And since we changed the direction, the sign changed, and since we multiplied by 1/2, it changed in magnitude by 1/2. Well, now that we've done that, we'll find that we've run out of equations up here, and so this better add together to give us our target equation, this equation here. It better add together to give that, otherwise we didn't do something correctly. So we're going to add these equations together, and when we add those equations together, we're going to cancel out the 3 halves of a mole of O2, so we'll cancel those out, and then we're left with just what's left over here. When we add those equations, we'll also add the delta H values together. And so you'll see that we get a value of negative 867.7 kilojoules for the overall equation. And that's how we do it. All right, I'm going to go through another one, and then we'll go through the one that is on the in-class assignment. So let's do, oh, there we go. I put it in there again. So negative 867.7. All right, let's do another one. So here we've got the enthalpies of these 3 different equations. So hydrogen plus fluorine gives us HF. Carbon plus fluorine gives us CF4. Carbon plus hydrogen gives us C2H4. All right, and then here we've got our delta H values. And with those delta H values, we now want to figure out what the delta H is for this particular reaction. So again, we're going to start on the left and work our way across. All right, so C2H4, we look, which equation is that in? Well, that's in the third equation. So we're going to take that third equation. You'll notice that it is the correct number. We've got 1 there, but it's not on the correct side. That means that we need to take that third equation and turn it around. And when we turn it around, of course, we're going to change the sign of delta H. So now we've got negative 52.3. All right, next we've got fluorine. You'll notice that fluorine, F2, is in 2 different equations. When that happens, skip it and come back. And usually it takes care of itself. All right, now we've got CF4, so 2CF4. If we look, we've got CF4 in the second equation, and it is on the correct side, so it's on the right side of the equation, but it's not the correct number. To get it to the correct number, we're going to multiply this by 2. So we'll multiply that by 2, so we'll get 2 times 1 is 2, 2 times 2 is 4, and 2 times 1 is 2. We'll also multiply the delta H by 2, and that gives us negative 1360 kilojoules. Finally, we want to do HF. HF is only in one equation. It's in the one that's up top. And it is on the correct side, so we don't need to change the direction, but we do need to multiply that first equation by 2 so that the coefficient becomes 4. When we multiply it by 2, we'll get 2 times 1 is 2, 2 times 1 is 2, and 2 times 2 is 4. And then we'll also multiply this by 2. 2 times 537, negative 537 is negative 1074. All right. And you'll notice that when we did that, that the fluorines did work out. It did balance out. So we're going to add these equations together and cancel out things that will cancel out. So you'll see that the carbon, let's see, the hydrogen cancels out and the carbon cancels out. And then here you'll see when we add the equations together, we get C2H4 plus 6 F2s gives us 2 CF4s and 4 HFs. And when we add those delta H's together, we will get negative 2486 kilojoules. So let's look at number 64 on the in-class assignment. All right, so our target equation is down here at the bottom. We've got our 3 component equations, and you can just read through those and see those. All right, we want to look, again, we're going to start on the left and work our way over. We want to look here first. So N2O, and we look up here and see where is N2O. Well, N2O is in the 3rd equation. So we're going to take that equation and use that to recreate this N2O. You'll notice here that it is on the correct side, so it is on the reactant side. However, you'll notice that it is not the right number. So we're going to take that and multiply that 3rd equation by 1/2. And so when we do that, we will get N2O gas gets converted into N2 gas plus 1/2 of a mole of O2 gas. And that has a delta H value of half that number, so negative 81.6 kilojoules. All right, so we've taken care of the N2O. Now for NO2. Well, again, we're going to go back and look, where is NO2? It's only in the 2nd equation, so we can use that. Since it's only in the 2nd equation, you'll notice that we've got NO2 here. It is on the wrong side. It's on the right side of the equation. We want it on the left, so we're going to have to flip it, which means we'll change the sign. But you'll also notice that here we've got 2. We only want 1 mole of it, so we're going to have to multiply it by 1/2. So we're going to change the direction and multiply by 1/2. So when we change the direction, so we get NO2 gas, and that gives us NO gas plus 1/2 of a mole of O2 gas. And then finally, writing our delta H. So we changed the direction, that made it positive, and then we multiplied by 1/2. And here, let's see, 113.1 times 0.5, and that gives us, so positive 56.55. All right, for the last one, this is a little bit tricky. You'll notice here that we've got 3 moles of NO on the right side, and on the first equation, we've got 2 moles of NO on the right side. You might think, oh, I just need to multiply that by 1.5. However, if you look closely, we already have 1 of the moles of NO accounted for. So since NO shows up in 2 equations, we need to account for that. So we only need 2 more moles of NO to make this work. So we're just going to take that equation. The NO is on the correct side, and we only need 2 more. So we're just going to take it and write it down again. So we'll put N2 gas plus O2 gas, and that gives us 2NO gas. And since we didn't change anything, that number will stay exactly the same. So positive 180.7 kilojoules. All right. So now let's see if things cancel out. All right. Well, we've got 1 mole of N2, 1 mole of N2 on each side, so that cancels out. We've got 1 mole of O2 and then half a mole and half a mole of O2 there, so those cancel out. And what we're left over with is N2O, so N2O gas plus NO2 gas gives us 3NO gas. And the delta H is simply going to be the sum of these three things. So let's clear all that. We'll do negative 81.6 plus 56.55 plus 180.7. And that gives us positive 155.65. Now, we should probably check our sig figs here. We've got tenths place, hundredths place, tenths place. So we're going to take that and round it to the tenths place. So we'll put positive 155.7 kilojoules. So 155.7 kilojoules. All right, that is Hess's law. I definitely recommend practicing a lot with Hess's law so that you get good at it. So let's switch back, and we're going to look at the concept that's called enthalpy of formation. The enthalpy of formation is defined as the enthalpy change for a reaction in which a compound is made from its constituent elements in their elemental forms. What that means is it is the enthalpy to form the substance from their elements in their elemental forms. And to do this, you will need to have the values for the enthalpy of formation, and you will also need to know what the elements are in their elemental forms. Now, I've got several here that are listed where we've got the enthalpy of formation for these substances. From here we've got acetylene, ammonia, benzene, so on and so forth. And on problem number 67, we're going to do a couple of examples of these. And so we'll switch over here to number 67. So I'm going to switch over here where I've got Appendix C, and let me make Appendix C bigger here for just a moment for purposes of looking at this. So on Appendix C, we've got the thermodynamic quantities for selected substances, and so you'll see a whole bunch of different substances here. And then you've got the delta H of formation as our first column. The second column is the delta G of formation. Delta G is a quantity we'll talk about in the second semester. And then here we have standard molar entropy as the third. That's also something we'll talk about in the second semester. So we're primarily interested in these numbers. You'll notice that each element has one thing that has a delta H of formation of 0. And that's because that is that element in its elemental form. And so since the delta H of formation is defined as the element in its elemental form, then that means if you're forming it from itself and it's in that same state, then it's going to have a delta H value of 0. So I am going to, I'm going to leave that open like that. And we are going to look at these substances. Let me scroll down. We'll find nitrogen and hydrogen. There's hydrogen. Well, nitrogen's in there somewhere. So let's do this first one. So here we've got ammonia. Ammonia, NH3. Well, the elemental form of nitrogen is N2 gas. And the elemental form of hydrogen is H2 gas. Now, in order for this to work, in order for the equation here to match the enthalpy of formation, two things have to be true. One is that the things over on the left have to be their elemental form of those elements. In other words, when you go look at the list on Appendix C, then you'll find that it's the thing that has an enthalpy of formation of 0. So here, nitrogen N2 has an enthalpy of formation of 0. The other thing is that the coefficient for your product has to be 1. That may mean that you have fractional values over here, and we'll definitely find that that is the case, that in order to get 1 mole of nitrogen atoms, we need half a mole of nitrogen molecules. Similarly, for the hydrogen, we're going to need 3/2 of a mole for that. Now, I am going to go ahead and make that just a little bit bigger. We're going to scroll down and we'll find nitrogen. And you'll see right here we have NH3AQ, and it has an enthalpy. Oh, we don't want AQ, we want gas. Has an enthalpy formation of negative 46.19. So negative 46.19. And the units for that are going to be in kilojoules per mole. So that'll be in kilojoules per mole. All right, so again, the requirements, you look up this value on your table, and then these values over here are, make this a little bit smaller. All right, so these values over here on the left have to be their elements in their elemental form, and it's okay if they have fractional values there. Let's look at this one. So rubidium, elemental rubidium, you know from the periodic table, it is a solid. So we'll have Rb solid. And since there's one rubidium atom, we're going to have a coefficient of 1 there for that. For chlorine, elemental chlorine, it's one of the diatomics. So it is Cl2 gas. And we'll need half a mole of that to get 1 mole of chlorine atoms. And then finally, for the oxygen, we already know that oxygen is O2 gas. And to get 3 there, we're going to need 3/2 of a mole of that. Now, I'll come over here and we'll scroll over to rubidium. There it is, rubidium chlorate. And you'll see the number there is negative 392.4. So negative 392.4 kilojoules per mole. All right, now for this last one, we already know about nitrogen. Nitrogen is N2 gas. And since we've got 2 nitrogen atoms here, we need a whole mole. We need 2 moles of nitrogen atoms, so we're going to have 1 mole of the N2 gas. So we'll leave that with a coefficient of 1. For hydrogen, we need 4 moles of hydrogen atom, so we're going to have 2 moles of hydrogen gas. And then for oxygen, we'll have 3/2 a mole of O2 gas. And then we'll look up what that is. And let's see, it's ammonium nitrate. It looks like it's right there. Negative 365.6. So negative 365.6 kilojoules per mole. All right, so those are the enthalpies of formation. So those are the enthalpies of formation. All right. I am going to minimize that, get that out of the way. And we're going to look at how it is that we use these enthalpies of formation. So how it is we go about using these enthalpies of formation. All right, so from the enthalpy of formation, so here, this is the enthalpy of formation for propane, this is for carbon dioxide, and this one is for water. These are values that we could look up in Appendix C. And we want to find the heat of this reaction. So really, this is just a Hess's law problem. So just like what we did before, we're going to take C3H8. We'll see C3H8 is that first equation. It's not on the correct side, so we'll need to flip the direction, but it is the correct number. So we'll just, we will change it. We'll change it to positive 103.85. For oxygen, you'll see that oxygen is in two different equations here. So we're going to skip that and it'll sort of fix itself. And then for carbon dioxide, so here's carbon dioxide. It is on the correct side, so we don't need to flip it, but we do need to change it. We need to multiply that by 3. So we're going to multiply that second equation by 3, and we'll also, of course, multiply the delta H by 3. Then finally, for the water, we've got 4 of those. It is on the correct side, but we need to multiply by 4 in that third equation. So we're going to multiply that third equation by 4. And now we will add those equations together. You'll notice that the carbon cancels out and the hydrogen cancels out. And then we end up with the 5 moles of O2 gas. When we add those together, we'll get a delta H of the reaction that is equal to negative 2220.0. That's after we round to the 10th place there. So negative 2220.0 kilojoules. Now, that is pretty convenient because as long as we have the enthalpies of formations of these substances, then we can get the overall enthalpy of this reaction without even having to do the reaction. Pretty cool. However, there's a shortcut, and here is our shortcut. All right, apparently I had some extra lines going on there. Not sure what happened there. So, so here with our shortcut, we can do this. We can do that delta H of our reaction is going to be the sum of all the enthalpies of formations of the products minus the sum of all the enthalpies of formations of our reactants. At first glance, this looks really like a really complicated equation. I think mostly because it's got 2 Greek letters in it. We've got the sigmas and the deltas, but it's not too bad. The deltas just mean change, and change in enthalpy of formation. We've already talked about that. And sigma just means added up. So we're going to add together all of the enthalpies of formations of our products and the enthalpies of formations of our reactants, and we'll take the difference. The N and the M just account for the coefficients in the balanced chemical equation. So this is how we use it. So here it's that the same equation that we were talking about just a moment ago. And here are the enthalpies of formations for each of those substances. And so we'll do the sum of the products. So we'll do the coefficient times the enthalpy of formation for carbon dioxide, the coefficient 4 times the enthalpy of formation for water, minus the reactants, and so 1 times that 1, there's an implied 1 there, times the coefficient or the enthalpy of formation for the propane, and then the same thing for the oxygen. Since if it's an element in its elemental form, and be careful about this, it has to be the right state. If it's an element in its elemental form, it'll have an enthalpy of formation of 0. So products minus reactants. So there are those parts of the numbers. And then finally, we get this, negative 2219.97. However, if we round to the 10th place, we're going to get negative 2220.0. So we're now going to switch over. All right, we're going to switch over here. And we're going to use Appendix C to write down the enthalpies of formation of these directly underneath. I don't know what those values are, but that's easy enough to figure out. Let's see. I'm going to switch over here, and I'm just going to make this big. And switch back over here. All right, so we'll do sulfur. So sulfur dioxide. There it is. Sulfur dioxide has an enthalpy of formation of negative 296.9. So negative 296.9. And then for sulfur trioxide, negative 395.2. And that's kilojoules per mole. And then the oxygen is going to be 0. And I'm going to write these all down. So now we'll go back. All right, I'm not sure why I'm getting that loud sound there, but that's okay. All right, so now we've got the enthalpies of formations of these, and we will calculate the enthalpy. So delta H, products minus reactants. So we're going to have 2 moles, and I'm going to write out the units this time, and then after that I'm not going to write the units. So 2 moles times negative 395.2 kilojoules per mole, all right, minus the reactants, so 2 moles times negative 296.9 kilojoules per mole, plus 1 times 0, and it doesn't matter what the units are there because that's 0. Okay, so we'll clear all that. We'll get 2 times negative 395.2. I'll go ahead and enter there, and I'll get a subtotal of negative 790.4. And then we have minus, and this is going to be a negative number as well, so 2 times negative 296.9, and so that's negative 593.8. All right, so I'm going to go up and grab that number minus that number, and we'll get negative 196.6 kilojoules. So negative 196.6 kilojoules. All right, and so that is the enthalpy of that particular reaction. All right, so we need to look up the delta H of formation for these other things. You'll see that none of these are their elements in their elemental forms. So we're going to need to look those up individually. And so I'm going to do this vertical split screen here so I can just write these down as we find them, and you'll be able to see me do it. All right, so silicon. All right, so silicon chloride, so negative 640.1. For water, we'll do the water here in a minute. Let's do the silicon dioxide. So silicon dioxide solid, negative 910.9. So negative 910.9. And then we'll do water. So I need to go up to oxygen. H2O, and it is H2O liquid. Make sure you pay attention to those 8. So negative 285.83. Might as well put the right number there. So negative 285.83. And then for the HCl, that's going to be under chlorine. And HCl, and it is HCl gas, negative 92.30. So negative 92.30. And all of those are in kilojoules per mole. All right, now that we've done that, let's get rid of that document. And we'll solve for delta H. So delta H, and here I'm not going to put the units, I'm just going to put the numbers. So for our products, 1 times negative 910.9 plus 4 times 92.30. And then for our reactants, we've got 1 times negative 640.1 and 2 times negative 285.83. All right. And I'm going to do subtotals of each of these. So 1 times negative 910.9 plus 4 times 90. Oh, that's negative 92. I'm glad I saw that. Negative 92 there. That's a negative. Negative 92.30. All right, so that part is negative 1280.1. So minus, and then we have negative 640.1, and that's times 1, plus 2 times negative 285.83. And that is negative 1211.76. All right, we're going to go up here. So we'll grab that number minus our previous number. And you'll see that we get negative 68.34. Now, as far as significant figures, this goes out to the tenths place. That one goes out to the hundredths place. So we're going to round that to the tenths place. So we're going to call that negative 68.3 kilojoules. All right. So what we know from both of these is that these are both exothermic reactions. And I'm going to double check my math on each of these. Yes. All right. Just checking my key there to make sure I didn't goof it up. Okay. So we're going to go back over here. I'm going to minimize that. And we're done with the in-class assignment problem. We do have just 2 more little things to look at. And that is in section 9, we have the bit about caloric food values. And there's a pretty good chance if you've taken a health class that you're familiar with this. What we call a food calorie, which is a calorie with an uppercase C, and you'll see that there it has the uppercase C, calories. That is in chemistry a kilocalorie. So we'll find that carbohydrates have 4 kilocalories per gram, and these are approximate numbers. It doesn't matter whether they come from sugars or starches or grains or whatever, but they will all come out the same there. So 4 kilocalories per gram. Let's see, for proteins, proteins are also 4 kilocalories per gram. Again, it doesn't much matter what kind of protein. It will still have the same fuel value. Fats and lipids, they're all going to be about 9 kilocalories per gram. And again, it doesn't matter whether it's a saturated or unsaturated or, a trans fat that's been hydrogenated. Regardless of what it is, it's still going to be 9 kilocalories per gram. Some of those are healthier for you, like polyunsaturated fats are better for you. But this isn't a health class, and I'm not going to go into that. There is one more that I want to mention, and that is that something not listed on your typical food label, nutritional facts label, and that's alcohol. And alcohol has a fuel value of 7 kilocalories per gram. These are hidden calories that are often not listed. It will have the total, usually listed in the total calories if you have an alcoholic beverage, if it lists the calories. But they don't put them on the label, and they can't put them on the label. So I think it's good to be aware that those calories are there, because that can turn into a significant source of calories for somebody who is not aware of that. And a drink or two a day, and you could end up getting several hundred extra calories that you did not realize were there. So something to be aware of. All right, we also want to look at energy and fuels. So we'll find that in the United States, the vast majority of energy that we use comes from fossil fuels. Fossil fuels are going to include petroleum, which is oil, natural gas, and coal. And you'll find that the vast majority of the energy that we use in the country comes from these three. Most of the petroleum goes into the transportation industry for things like gasoline and diesel fuel and various things of that sort. Natural gas, a lot of that goes into either generating electricity or into actually directly heating your home. If you've got natural gas in your home, then that would be the source there. And then coal, much of the coal either goes in directly into industrial use or generating electricity at a coal-fired power plant. Now, other sources that are not fossil fuels are going to include nuclear. About 8.6% of our total energy usage in the United States comes from nuclear, and about 9.9% comes from renewable energy. Now, over the past several editions of the textbook, this percentage has gone up, but you'll see that it's still at about 10%. If you're looking at these, the source of fossil fuels that we use the most, source of energy that we use the most, comes from petroleum, so from oil. And like I said, much of that goes into the transportation industry for airplanes and trucks and cars, although some of it goes into heating oil. And then the one that's most abundant, interestingly, is coal. So we have so much coal in the United States that we could just keep burning coal for hundreds of years and never really run out. The downside is that when you burn coal, it does produce quite a bit of pollution and quite a bit of carbon dioxide, which is a key contributor to global warming. So coal is probably something we don't, even though we have lots of resources, we probably do not want to extend the amount of coal that we're using. So again, the one that we use the most is petroleum, which is oil, and the one that we have the most of is coal. And then just to kind of give you an idea of what the fuel value of different fuels are, we've got this little graph here. So like if you burn wood, since wood wood has quite a bit of oxygen in it. It's got complex. They're not carbohydrates, but it's got cellulose in it. And when you burn cellulose, there's already quite a bit of oxygen in there, so you don't get quite as much energy out of it because the carbons are already partially oxidized. If you go to things like charcoal or coal, they have a lot higher percentage of carbon in them, and so you get a lot more fuel value out of them. Crude oil, again, it's a higher percentage of coal in them or carbon in them, so you get a higher fuel value out of them. Interestingly, hydrogen is listed here. It's not a fuel source in and of itself because naturally occurring hydrogen, H2, does not exist in that form on Earth, at least, where you just get H2 gas. You have to produce hydrogen from some other fuel source. So that's a little bit misleading that that's on the list, but kind of interesting. All right, well, that is the end of Chapter 5. So there we go. That's the end of Chapter 5. And so that will also be the end of the content for the third exam.